Okay, so let me start with a recap of the previous video. This was a expression for the cross product of two vectors. As you can see, it's a bit of a mess, and you're not necessarily expected to remember it in under this presentation. Now, as a special case of this formula, you could consider the situation where both of the vectors belong to the xy plane, meaning that the third coordinate is 0. And what you notice there is that the cross product takes a very simple expression because, the vector has to be perpendicular to u and v, but u and v are both on the xy plane, so that means that it has to be pointing along the z-axis. So that's why the first two coordinates, or the first two entries for the vector, become 0. And then you find this expression on the third entry, okay, which is, just some interesting combination of the coordinates of the first vector and the coordinates of the second vector. But as a way to remember it, you can think of taking these two and making an arrange of a 2 by 2 arrange, which is known usually as a matrix. And then there's a quantity, again, like you can think of a matrix as a new object in the same way in which functions are mathematical objects or vectors are mathematical objects. So whenever you have this arrangement of 2 by 2 of a matrix, you can extract from it a number. And this number is in particular is called a determinant. And so the determinant of this matrix happens to be x1, y2 minus y1, x2. And the way in which you compute it is by doing the products along the diagonal, so x1, y2, y1, x2, and then subtracting the answer. Okay? Now the point is that what I'll explain to you in a moment, like what's a perspective, is that the cross product in a sense consists of 3 mini determinants. Okay, but before doing that, let me just do a couple of examples with determinants of 2 by 2 matrices so that you see how it works. So say the determinant of 1, 2, negative 1, 7 is just 1 times 7 minus 2 times negative 1. So this becomes 7 plus 2, which is 9. Okay? Or for example, the determinant of 7, 5, negative 1, 2, that's 7 times 2 minus, let's call this 1 times 5, so that gives you 14 minus 5, which is 9. Okay, so in practice, computing determinants of 2 by 2 matrices is not that difficult. Now, one way to think about the determinant of a 2 by 2 matrix, again, is that remember that the norm of the cross product, let me put it like this. So the norm of the cross product was the area of the parallelogram, right? So remember that there's let's see, I don't like this. Do I like this picture? Oh yeah, well, kind of. So the norm of the cross product, in this case, what would be the norm? Well, the first two entries are 0, so it's just the square root. It's just really the absolute value of this number. on the other hand, we know that you can make a parallelogram with these two vectors, and the area was the same as the norm of the cross product. And so what that means, if you compare this with that, that tells you that the absolute value of the determinant the absolute value of this number is precisely the area of the parallelogram. So is the area of the parallelogram. Determined by the vectors x1, y1 and x2, y2. Okay? So what that tells you is that determinants secretly compute like some areas. Determinants of 2 by 2 matrices compute like areas of certain parallelograms, and then the point is that the cross product then can be regarded as giving you the information from 3 parallelograms. Okay, so what are those 3 parallelograms? Well, no, they won't be very easy to draw, but let me attempt at drawing them. So let's say here's U, here's V. Now the point is that they no longer belong to any particular plane, but still you can think of the shadow that each of the vectors makes along each corresponding plane. So say if you think about like this is like an analog of like the orthogonal projections that we discussed before. Okay, so when you consider the shadows, you get a couple like what I'm trying to say is like you can sort of create shadows on each plane. So this is like a shadow on the xy plane. There will be some other shadow on the zx plane, and there's another shadow here, which I will try to draw because it will get too confusing. But the point is that then there's like an area 1. Here there's a mini parallelogram that you can form with the shadows. There's another parallelogram that you can form with the shadows. And there's another one here. Let me see if I can make it work. Well, this is very heuristic, but so there are like 3 parallelograms happening in this picture, and this one has to do okay, there was a small glitch, but I was just saying that I was going to relabel the signed areas, again signed because they can be positive or negative. I'm going to relabel these areas according to the plane to which they belong. So for example, this parallelogram belongs to the xy plane, so I'm going to use A of xy to denote that area. And that is a quantity, the number that goes in front of the third vector. The area of the xz plane is the one that goes in the middle, and the area of the parallelogram that you get on the yz plane is the one that goes first. Okay? So you should think of the cross product as recording 3 signed areas. Like you have these vectors, they make shadows on each plane, and you create mini parallelograms, and that's the area that you care about. Now, but it's still okay. So this gives you some more insight on what the cross product is telling you, but it still doesn't help you for computing it. And so the point is that in order to really memorize this formula, which is what we want, we will do a small trick, which is compute the determinant of a 3 by 3 matrix. Okay? So here's one way to think of the determinant of a 2 by 2 matrix. You can think of this array as assigning to this array a sequence of pluses and minus signs. So plus, minus, minus, plus. So they just alternate from between each other. And so what you're doing is in a sense, this will, let me backtrack here because the formula is a bit too elementary, but this is what we're about to do for the 3 by 3 case. So if you have, say, A, B, C, D, F, D, E, F, G, H, I, imagine that this is an array of three vectors of size 3, so it's a 3 by 3 array. So what we're going to do is plus, minus, plus, minus, plus, minus, plus, minus, plus. So what you do is basically assign a plus and minus to each entry, alternating. You always start with a plus on the upper left corner. And then the formula for the determinant. Okay, so there's again like this determinant, like it does have some geometric meaning. The point is that once you have 3 vectors in space, you can form like a parallelepiped, and the volume of that parallelepiped is the absolute value of this quantity. Okay, but we won't play with that interpretation directly. For now, it's just like a useful way to remember the formula that we care about. So what we will do is, and again, if you take linear algebra class, you will realize that there are many ways to do this. But what we do is extract from the first row the entries. So you'll say, oh, this is plus A minus B plus C, right? So that gives you the signs. And then you put a tiny determinant on each of a 2 by 2 determinant next to each coefficient. So which determinant you put? Well, here I'm deleting the first row, first column, because that's where A belongs. So you get a 2 by 2 matrix, which is E, F, H, I. Here, then I'm deleting the first row, second column, because that's where B belongs. So you get determinant D, F, G, I. And finally, for the last one, I'm deleting the first row, third column, and so you get a determinant of D, E, G, H. So you get, in the end, and the point is that the individual determinants you know how to compute. So EI minus FH minus B DI minus FG plus C DH minus EG. Okay, so this will be a number. For example, what is for this particular array? What's the number? Well, again, is plus 1, the determinant that you get by erasing first column, first row. So 1, 2, 1, 2, minus, oh, yes, yeah, right. This can be confusing. You always have to take, so you put a minus from the formula. This one already has a minus, so you put something like this. Plus 2, the determinant of 3, 1, 1, 1. And you'll see that this gives you 0 plus 1. Okay, so you get 0. This gives you 6 minus 2, that's 4. There's some plus here, so you get plus 4. And then you get 3 minus 1, that's 2, plus 2, so you get 4. So this gives you 8. Okay? So this determinant of the 3 by 3 matrix is 8. And now that we have mastered the formula for the determinant, I can tell you, notice that like there's an incredible similarity between these combinations, right? If only A, B, and C play the role of I, J, and K, they will look almost the same, and basically that's the point. And this is really where we were what we were after. So the formula for the cross product, the final formula that you actually need to know how to use, is that, and this is somehow a bit formal, but the idea is that if you want to do the cross product of two vectors, x1, y1, z1, and x2, y2, c2, then the cross product of u cross v can be computed by creating a 3 by 3 matrix where you will put the first vector in the second row, the second vector in the third row, and the univectors I, J, and K in the first row. Now, the point is that strictly speaking, you cannot do that because on a matrix you can only place numbers, so this is a bit formal. But if you just follow the logic, you get plus I times a determinant. Remember, delete first row, first column. Then minus j times a determinant. Remember, delete first row, second column now. Plus k times a determinant where you now delete first row, third column. Okay? So you end up getting what? You get plus I. You can just move the I around, so you get y1 c2 minus c1 y2 I, which is exactly what we had here. Then you get minus j, so you get x1 c2 minus c1 x2. Notice that if you move the sign inside the parenthesis, that's how you get the second term. And finally, you get plus k x1 y2 minus y1 x2. Okay? So essentially what this means is that in practice you can compute the formula of a cross product by creating this 3x3 array. So let's finish this off with a concrete example. So say if you wanted to find the cross product between 1, 2, 3 and -1, 1, 2, what you would do is do a determinant. Again, you put I, j, and k on the first row, and then you just copy these two. And you do plus minus plus, so you get plus I, determinant of 2, 3, 1, 2, minus j, determinant of 1, 3, -1, 2, plus k, determinant of 1, 2, -1, 1. And that gives you 4 minus 3, that's 1, so 1j, minus 2 minus minus becomes plus 3, so this gives you 5, and then there's a minus here, so minus 5j plus 1 minus minus becomes plus 2, so this 1 plus 2 is 3. Okay, and the point is that this is a lot easier to do than just trying to memorize this formula directly. Okay, so this is basically the conclusion of the first topic about vectors. What we will start discussing next time is lines and planes.